Hello and welcome back to question 2. You know the drill. Let's start with step 0. Firstly, is the population normally distributed? Yes, you can read from the first sentence over here. Next, do I know the population variance? Yes, I'm given the standard deviation. I just need to square that to get the variance. Other important numbers to take note: the claimed population mean is 250 grams, observed sample mean is 248 grams, and the sample size is 50. Let's write that somewhere on our foolscap paper in pencil. Great. Now we need to define the random variable x to represent the mass of an apple in this orchard. We are now ready to move on to step 1. In step 1, we have to write down our two hypotheses. The null hypothesis comes from the farmer's claim that the average mass of all his apples is 250 grams. We did a sample of 50 apples and found that the sample mean is lower than 250, so we have reason to believe that the farmer could be overstating the masses of his apples. And we're going to do this test at a 5% level of significance. It is at this point we have all the information from the question fully transferred into the foolscap paper. We no longer need to refer to the question paper. Let's move on to step 2. Welcome back to step 2. In order to conduct the test, we first have to assume that what the farmer said is true. Working under that assumption, then our sampling mean variable will be normally distributed. The mean is 250, variance is 100 over 50. Now that is just 2. This is the step that most students struggle with because they do not understand what's going on here. Let me very quickly explain the meaning of these two very short sentences. In order to explain what step 2 means, I had to draw two distributions, one in green and one in white. The one in green represents the population of the apples. The standard deviation of 10, meaning that 68% of all the apples in the orchard are between 240 to 260 grams. Assuming what the farmer claims to be true, that is the center of this distribution is 250, then I can say with absolute confidence, my sample means will be centered at 250, and if I move square root 2 to the left and square root 2 to the right, this will capture 68% of possible sample means results. This is the meaning of these two lines over here. Assuming that what you said is true, that the center is here, then my sample mean distribution will also be centered around the same mean with a reduced variance. Then we need to look at our observed sample mean. What is the statistical probability of getting 248 grams here? Is it something that is very unlikely or acceptable? And that depends on our level of significance. Let's take a look at the next step of step 2. We take our sample mean variable and convert it into the standard normal variable. We use this very simple formula to convert that. How does that work? First of all, we will take x bar. X bar represents all the possible sample means and minus all of them by 250. The effect of that is to shift every single value 250 to the left. That shifts our distribution so that the mean is 0. Next, if you divide by the standard deviation, which is square root 2, all the points that are square root 2 will now be a distance of 1 away from the mean. So the results of applying this formula really is just a transformation of graph. The subtraction of mu is really just a shift in the negative x-axis direction in this case. And then dividing by the standard deviation is a scaling in a direction that's parallel to the x-axis. And why do we do this? And that's because a long time ago, we did not have graphing calculators. We had to depend on lookup tables. Let's move on to step 3a, how we can conduct the test using the z value and the critical region. Welcome back to step 3a. In order to calculate our test statistics z, let's fill in the values. X bar is our observed sample mean of 248, mu is 250. Now we're going to divide by sigma over square root n. So sigma square over n is the variance, which means sigma over square root n is the standard deviation. The standard deviation is square root 2. This will give us negative square root 2. So that is our test statistic z. Let's find out where is our critical region. To find the critical region, we have to use the inverse norm function on the graphing calculator. So this is what you should be inputting on the inverse norm function. When you press enter, you get this value, negative 1.6449 phi SF. Now, you can also do this using the MF26. Let me show you quickly how it can be done. Go to page 7 of your MF26. This diagram over here will show you how to use this lookup table. For example, I want 95% here, which means 5% on the right tail. Then I'm looking for a value that's very close to 0.95. Perhaps this one. So if you trace to the left, you find this is 1.6. If you trace upwards, this is 4. So this is 1.64. At a z value of 1.64, you're going to get 0.9495 area under the graph. To get it exactly 0.95, I need to add 0.0005. To add 0.0005, I need to go over here. Okay, and I need to add 5 to this, which means that at 1.645, I'm getting about 0.95. which means that by symmetry, if I want the 5% not to be on the right tail but on the left tail, I just need to flip and make this a negative 1.645. This is how you can use the lookup table. In fact, they actually have simplified it for you. So if you want an area of 95%, they actually have looked that out for you over here, 1.645. And if you want it to be on the left tail instead, then you have to use a negative value. So this is how you can use the MF26 instead of using your GC. So now that we have the critical region, let's update our sketch. So the critical region is going to be the left tail. And as you can see, since our test statistic is not within the critical region, we do not reject H0. Now let's look at step 3b. How can we conduct the same test, but just purely using the calculator and obtaining the p-value? I'll come back to step 3b. In order to conduct the test using the p-value, you have to input these things into your graphing calculator under z-test, and you'll get this. So our p-value is 0.078650 SF. And since this value is greater than the level of significance, which is 0.05, we do not reject H0. So let's look at step 4, how we can conclude this question. In conclusion, we can either say A or B, depending on which step you use in step 3. The test statistic, which is the one in pink, has fallen outside the critical region, the one in orange. Therefore, we do not reject H0 at the 5% level of significance. Or if you like short and sharp, you can go with p-value, method 3b. You can just say that the p-value is greater than the level of significance, 0.05. Therefore, we do not reject H0 at the 5% level of significance. And remember to answer the context of the question. Our concluding statement will be, there is insufficient evidence to conclude that the farmer has overstated the mean. That's the end of question 2, and I'll see you in question 3.